Hello, beautiful viewers. Welcome to the last edition of my lesson on the gravitational field. It has really been a worthwhile session with you, my lovely viewers, from the very first to the fourth session. Thank you for being there and happy listening. As we have dwelled greatly on various subtopics under this universal topic, we shall conclude with the differences between our small g, which is our gravitational field strength, and our big G, which is our gravitational constant, respectively. The two terms have always been oftentimes confused to mean the same thing, but this lesson will tell you the differences between the two of them. And these are the differences I'm about to show you. So let's see them. The learning outcomes for this lesson will be to list the differences between our gravitational field strength and our gravitational constant. To define the escape velocity, yes, we'll be talking about the escape velocity, and to also solve related problems under the escape. Now, the differences between our gravitational field intensity and our gravitational constant, I've listed them out in a tabular form. So our gravitational field strength is what we denote by our small g, while our big G is called the gravitational constant. The second difference is that G varies from place to place on the Earth's surface. We talked about the variations in G in our previous lesson. So that alone serves as a difference between gravitational field strength and gravitational constant. So while G varies from place to place on the Earth's surface, our big G is constant over the Earth's surface. Our G is a vector quantity, our small g called the gravitational field strength, while our big G is a scalar quantity. The unit of gravitational field strength is Newton per kilogram or meters per second square, since it is also referred to as the acceleration due to gravity. So it takes 2 units, while our big G, which is called the gravitational constant, has its unit to be Newton meter square per kilogram square. So these 4 differences is enough for you to memorize or understand and be able to confidently beat your chest anytime you are asked the differences between our gravitational field strength or the differences between our gravitational field strength and our gravitational constant. Now we'll be talking about the escape velocity. What do you think the word escape means? The dictionary gives us the word escape to mean to break free, to get away. So if you can have the idea of what escape means, then that will not be difficult to define what escape velocity means. Or to just define the word escape velocity. So escape velocity is that minimum velocity required by an object to leave the gravitational influence of the Earth permanently. You can see I put in brackets the astronomical body. So we are talking about the planet Earth here, so it could mean any other planet. So once any object is able to leave the gravitational influence of a planet with a minimum velocity, we call that minimum velocity the escape velocity. Going by the diagram here, the object in question here is the rocket. You can see the rocket there leaving the Earth with a certain amount of velocity. So that velocity in question there is the escape velocity, and it is given by the formula V is equal to square root of 2gm all over r, or square root of 2gr. And this second formula is as a result of substituting the formula small g is equal to big gm all over r square into the formula, the first formula given above. So multiplying both sides by the big R, our small g big R becomes equal to gm big gm all over r. So any of these two formulae can be used in solving our escape velocity. That is the example. Assuming the mass of the moon is 7.4 times 10 raised power 22 kilograms, and its radius is 1.7 times 10 raised power 3 kilometers. Calculate the escape velocity from the moon's surface. Take g is equal to 6.7 times 10 raised power minus 11 Newton meter square per kilogram square. So using our formula, we have v is equal to square root of 2gm all over r. This formula is ideal because of the parameters given. So we can see that the value of radius given there is a kilometer. So it is mandatory for us to convert from kilometers to meters. And since 1 kilometer equals 1000 meters, we have our value there multiplied by 1000, and our final answer becomes 1.7 times 10 raised power 6 meters. So substituting into the formula, we have 2 times 6.7 times 10 raised power minus 11 times 7.4 times 10 raised power 22 all over 1.7 times 10 raised power 6. Dividing, we have square root of 5.8 times 10 raised power 6. Final answer gives us 2.4 times 10 raised power 3 meters per second. I'll need you to try your hands on this. Calculate the escape velocity of a satellite launched from the Earth's surface. Take small g is equal to 10 meters per second square, and the radius of the Earth to be 6.4 times 10 raised power 6 meters. Pretty simple, you will say. Good. So now that we have done justice to the topic as a whole, ranging from our gravitational force, gravitational field, Newton's universal law of gravitation, gravitational field intensity, the questions relating to gravitational field intensity, gravitational potential, questions relating to that, our differences between our gravitational field intensity and gravitational constant, and our gravitational potential, and of course our escape velocity. I know you can now confidently tackle any question whatsoever on gravitational field. So thank you for your time, and see you next time. Bye for now.